In section 12.4, we look at what's called a normal distribution. Many of you have probably heard about bell curves. This is a very specific bell curve called a normal curve. Normal curves happen in many situations once you have a large enough sample size. What makes a normal curve special is that the mean and the median are the same. In all of the problems that we've looked at so far, they have not been exactly the same. They may be very close, but they haven't been exactly the same. There are many natural situations that have normal distributions. If you were to look at the average weight for all American males, if you were to look at the heights for all American females, those types of things become normal distributions. As students, you have all taken some kind of standardized test. In Indiana, we had the I-STEP for many years. I forget what the new one is. The SAT, the ACT. Those standardized tests all have large enough groups of people that they have a normal distribution. If you know that your distribution is normal, then you know percentages that are always going to be true. The first thing I'm going to do is show you how those percentages work on a normal curve. But before we get started, we need to talk a little bit about notations. The first thing I want to talk about is this O with the tail off the top of it. That is the lowercase Greek letter sigma, and that is the symbol for standard deviation. Down below, we have this symbol with the X with the line over the top of it, and that is creatively given the name X bar, and that is the symbol for mean. When you have a normal curve, the center line is always the mean and the median. The first line to the right is one standard deviation bigger than the mean or median. The second line is two standard deviations bigger than the mean or the median. And the third line is three standard deviations bigger than the mean or the median. To the left, we have one standard deviation below the mean or median, two standard deviations below the mean or median, and the third line to the left is three standard deviations below the mean or median. Now that we have those numbers in place, let's talk about the percentages that are always true on normal curves. 68% of all data goes from the -1 to the +1. We say this within one standard deviation. 95% of all the data on a normal curve goes from the -2 to the +2, which we say is within two standard deviations. 99.7, if you think about that, that's a whole lot of the data, fall within three standard deviations. Now that we know those percentages, I'm going to break them down a little bit more. Your textbooks don't usually do this, but I think it makes it much easier to work with a normal curve if you break them down a little bit more. Remember that we know that 68% of all the data lie between the ones. This curve is perfectly symmetric. So in order for that to be equal on each side of the middle, that means that 34% of the data has to be from the mean to the +1 and the mean to the -1. we know that 95% of the data has to be within 2 standard deviations. We have already labeled 2 of those 4 segments that are covered by 95%. So if we take the 95 that we need in total and subtract the 68 that we have already used as labels, that leaves us with 27% for each of the next 2 sections. But this has to be symmetric, so we have to split it in half, which means that 13.5% of your data lies between the 1 and the 2 on each side. We further know that 99.7% of the data lies within 3 standard deviations. At this point, we have labeled 95% of the data. So if we take 99.7 minus 95, what's left is 4.7. That 4.7 is the total for both of these sections, but it has to be symmetric, so we're going to split that in half, which means that each section from the 2 to the 3, this means that from the 2 to the 3 on each side must be 2.35% of the data. The entire curve has to cover 100%. At this point, we have used 99.7, so if we take 100 minus 99.7, what's left is 0.3%. If we split that in half, that means that each of these tails is 0.15% of the data. These percentages are always true if you know that you have a normal distribution. For example 1, we are told that the 2010 ISTEP algebra exam had a mean score of 600 and a standard deviation of 100. This is real data that I got by looking online for that information. Those percentages that we talked about just before are always true. So every time you have a normal distribution problem, the first thing you're going to do is put those percentages in place. What will vary from problem to problem is the labels on the bottom. They are always problem specific. Remember that the mean and the median go on the center line. So because we are told the mean is 600, our center line label will be 600. The standard deviation is 100. So we are going to add 100s to the right and subtract 100s to the left. So the first bar to the right will be at 700, the second will be at 800, and the third will be at 900. Going to the left, we will have 500, 400, and 300. Then you are just going to be asked questions about that normal curve. What percent of the students who took the ISTEP had a score over 500? So we're going to look for where 500 falls on our normal curve. It's the first bar to the left. Everything over 500 is all of these sections together. Now keep in mind that 600 was in the middle. So that means from the 600 to the right has to be 50%. So if we take that 50% we know and add the 34% between 500 and 600, our answer will be 84%. For question B, you are asked what percent had a score less than 800. So look for the 800. It's the first bar or second bar to the right, and less than means we want all the stuff to the left of that. So you can add up all of those sections, or you could look at the fact that there's only 2 sections that are not included and take 100%, which is the whole curve, minus the 2.35 minus the 0.15, which gives you 100 minus 2.5, which is 97.5%. On question C, you are asked what percent of the scores are between 400 and 900. So we're going to go back up to our curve. 400 is here, 900 is here, and if we add up all of those sections, 34 plus 34 gives us 68, plus the 13.5 plus the 13.5 gives us 95. So we have 95 plus 2.35, which gives us 97.5%. Then the last question about this curve is D. And D is asking us what percent of the scores are over 600. Well, if we look at our curve, the 600 was the middle line. And remember, that's the mean or the median, both. So if it's exactly in the middle, what percent are over or to the right? That has to be 50%. In the next part of the notes, we are going to look at what is called the standard normal curve. Standard normal curves are used by statisticians frequently, and in order to be a standard normal curve, your mean equals 0 and your standard deviation equals 1. A z-score is a technique of converting any set of data to a standard normal curve. In order to do this, to find a z-score, you take the data value that you are given minus the mean. Sometimes you will get a negative and sometimes you will get a positive. This is okay. And you take that answer divided by the standard deviation. For example 2, you are told that a student on the 2010 I-STEP algebra exam had a score of 714. There's actually 2 questions here. First, find the z-score, and then secondly, what did you find? Well, a z-score for the score of 714. This is frequently how you will see it written. You'll see the letter Z and then a subscript for which score you are finding the z-score. Equals. Now remember, you take the score that you are given, which was 714, minus the mean for that data, which from the last problem we knew was 600, and then divide that by the standard deviation, which we know from the last problem is 100. Well, that gives us 114 over 100, and when we actually do that division, we get 1.14. So that's the answer for the z-score. And that's great, but what in the world is that? When you find a z-score, you are finding how many standard deviations the data value that you were given fell either above or below the mean or median. So in this particular case, a student with a score of 714 is 1.14 standard deviations. I'm just going to abbreviate here. Because our 1.14 was positive, we are going to say above the mean. On example 3, we are told that another student had a score of 546, and we are asked to find their z-score. The z-score for a I-STEP score of 546, we're going to take that score minus the mean over the standard deviation. Well, 546 minus 600 is negative 54, divided by 100 gives us negative 0.54. So even though it didn't ask us for this information on this question, just for practice, I'm going to write it out. What you just found in doing this problem is that a score of 546 is 0.54 standard deviations, again abbreviating, and because it was negative, we say below the mean. On example 4, you are asked to find the I-STEP score for a student who falls 2.5 standard deviations below the mean. Because we are told how much the student fell below the mean, we know the z-score of whatever they got on this test has to be negative, because it says below, 2.5. Now we're going to use the formula where the negative 2.5 is the answer that we got, and we are looking for what they originally earned on the test, so that's the x minus the mean from this test, which was 600, over the standard deviation, which is 100. Now we have a basic algebra equation to solve. We are going to multiply both sides by 100 to clear the fraction on the right. 100 times negative 2.5 gives me negative 250 equals x minus 600. Then we are going to add 600 on both sides, and we will now have that x equals 350. So this now tells me that the student's I-STEP score is 350. Very often, when you see statistics on the news, they tell you that this percentage of people liked this, or that percentage of people said yes to that. And they give you the percentage, but they don't give you the full information. The piece of information that they are not giving you frequently is called the margin of error. The The margin of error is a number that tells you basically how far off you might be on the data that you are reporting. There are businesses whose entire job is to take samples, ask people questions, and then figure out what percentage of people like this or don't like that. And they always use a margin of error. In the news, they don't think that people can understand that, so they frequently do not include it. There is a very technical formula for margin of error. We are not going to use the very technical formula. We are going to use a formula that is just an estimate. It is a quick and easy formula to use. The formula we are going to use is plus or minus 1 over the square root of n times 100%, where n is your sample size. So in example 5, we are told that we have a sample of 400. We want to find margin of error. And I abbreviate this again because I don't like to write all those words out. So for this problem, to estimate our margin of error, we are going to say plus or minus 1 over the square root of our sample size was 400. And then when we're done, we're going to take that times 100%. So taking the square root of 400, we get 20. So we have 1 over 20 times 100%. 1 over 20 is 0.05, which we are going to take times 100%. So what we have just found is that this margin of error, now remember, this is just a fast, easy way to estimate margin of error, is plus or minus 5%. Margin of error changes depending on the size of your sample. Let's think about this logically. If you ask more people a question, you are going to be closer to the true size of the population and therefore more accurate. The fewer people you ask a question, the less accurate you are. So, as sample size increases, margin of error will decrease. And vice versa, as sample size decreases, margin of error increases. The last thing that we need to talk about for this section is called a 95% confidence interval. When you see percentages given in the news, whether it's a newspaper or on TV, those percentages have been found using a 95% confidence interval. But again, most people don't have a clue in the world what that means, so the news doesn't include it because it would confuse too many people. A 95% confidence interval contains two pieces of information. It contains the percent who say yes to whatever question you're talking about, plus or minus the margin of error. On example 6, we are told that there were 1,000 adults asked the question of whether they dreaded going to the dentist. 41% said yes to this. We are asked to find the 95% confidence interval. So we have our percent who said yes, the first thing that we are supposed to have in a 95% confidence interval. What we don't have is the margin of error, but we have our formula that allows us to estimate margin of error. So the first thing we're going to do is find that margin of error. Remember, we take 1 divided by the square root of the sample size and then take the answer times 100%. So in this case, we are going to have 1 over the square root of 1,000 is approximately 31.623. We're going to take this times the 100%, do that division, and you will get 0.032 rounded times 100%. And then if you actually take those two times each other, you get 3.2%. So we have found the margin of error to be approximately 3.2%. We are not done with our question because our question was to find the 95% confidence interval. So our 95% confidence interval is the percent who said yes, which is 41, plus or minus 3.2%. If we do the subtraction and the addition that we see in that confidence interval, we will have an overall interval of 37.8% to 44.2%. So what that means is when we took our sample, 41% is what we got. That could be the right answer, but it could also be off a little bit. So what we know then, based on doing these calculations, is that 95% of all samples of the same size, so in this case, that is 1,000, would fall between the two numbers that we got, 37.8% and 44.2%.